Okay, so here we go. Welcome to chapter 18, our last chapter. I'm so excited that it's the last chapter. I hope you are too. Section 18.1, continuous probability models. Okay, here we're going to take a look at continuous random variables, continuous probability distributions, and cumulative distribution functions. This idea of the continuous random variable, we're going to continue. Get that pun? Continuous random variables. We're going to continue what we looked at in chapter 9 with those normal distributions, and we're going to take a look at more models like that. We're going to take a look at more scenarios where we're going to have a function y equals f of x. We're going to have some range of values, some a to b, and this area under there is going to be probability. So we're looking at a probability model for an experiment where the random variable is continuous. Right? These functions we're going to look at, we're going to give them a name. We're going to call these guys probability density functions. That's going to be that f of x, whatever that algebra is of that thing. And they have two requirements. One, that the function must be greater than, there's supposed to be a 0 in there. That's a weird typo. All right, I'm going to pause this, go fix that. Okay, it'll be fixed on your copy of it when you've downloaded it. But that function must be greater than 0 for all the x's in the interval that we care about. Now, that means it can go negative further over here, left of a, it could go negative further over here, right of b, but between a and b, it's got to be not negative. And the value of that integral, that area under that curve between a and b, must add up to 1. Okay? So this piece right here, that area, since it's a probability model, that area must add up to 1. Okay? So then if it meets those requirements, so if that x is a continuous random variable, and if we have a function f, and if we have an interval that works for it, and that function f is a probability model, then probabilities for x's in there, probabilities that x is between two values, is just the value of the integral. Okay? All right, our first example here asked us to show that this function is a probability density function on that interval. Right? Well, let's take a look at what's going on here. I have to show that it meets these two requirements right here. Right? Number one, I have to show that that function f of x is greater than or equal to 0 on the interval, or in the interval. For whatever reason, this author likes the word in the interval 1 to 3, and 2, that the integral from 1 to 3 of that function f of x dx is equal to 1. Okay? I'll tackle these one at a time. First, we'll do the first one, 1. So this is what I'm trying to show. Let's see, graph of this thing. That's a parabola opening up, right? It has an intercept at the origin. So that means from 1 to 3, it's definitely above the x-axis, so that's good. 2, I have to do that integral. I have to integrate from 1 to 3, 3/26 x squared dx, and hope that that's equal to 1. Now, hopefully, remember integration. Right? So let's see. The antiderivative of 3/26x is going to be 3/26 times x cubed over 3, and then I need to evaluate from 1 to 3. Right? I think those 3's right there are going to cancel, and I'm just going to get x cubed over 26 evaluated from 1 to 3. Okay, I'm going to drag it up over here. That's going to be 3 cubed over 26 minus 1 cubed over 26. 3 cubed is 27, so I've got 27 minus 1, both over 26. 26 over 26, that is indeed equal to 1. So yes, that is a valid probability density function on the interval 1 to 3. Okay. All right, our next example. Is there a constant k? So does there exist a value k? Is there a constant k to make that into a probability density function on the interval 2 to 7? Well, if it's a probability density function, then those two things are still going to be met. One, that function f of x will be greater than or equal to 0 on the interval, or in the interval, 2 to 7. And two, the integral from 2 to 7 of kx squared dx will be equal to 1. Now I know as long as I pick a k that's positive, that first one will be true, because that'll make it be a parabola opening up and I don't have to worry about it going negative. I'm not sure about that second one. I'm going to have to do some math to figure that out. All right, so I'm going to try to force this one to be true. So the integral from 2 to 7 of kx squared dx, and I want to set that equal to 1 and then solve for k. So I'm going to solve for my unknown. Right? Antiderivative of kx squared is going to be k times x cubed over 3, evaluated from 2 to 7. And again, I'm forcing this to be equal to 1. Okay? So that's going to give me, and I'm going to drag it up over here. That's going to give me k times 7 cubed over 3 minus k times 2 cubed over 3. And I want to set this equal to 1. I'm going to do a little bit of factoring on the left-hand side. I'm going to get k 7 cubed. What's 7 cubed? 7 cubed, I'm going to grab my calculator here. 7 cubed, I think that's 343, yeah. So I've got 343 minus 8 over 3 is equal to 1. 343 minus 8 is 335 over 3 is equal to 1. So then k is equal to 3 over 335. When we multiply a number by its reciprocal, the product is 1. Yeah, so there's the k that makes it work. It's a positive number, so that'll satisfy option number 1, and it makes the integral equal to 1. So that's the k that makes this guy a probability density function on that interval. Nice. All right, so given that, well, let's calculate some probabilities. A machine has a useful life from 4 to 9 years, and its life expectancy has a probability density function defined by that hot mess right there. Find the probability that the machine lasts longer than 6 years, less than 5 years, between 4 and 7 years. Well, I should be able to do this. I'm pretty good at math. Okay. This useful life of 4 to 9 years tells me that this probability density function is on the interval 4 to 9. Now, I don't have to check to make sure this is true because I'm told right here that it is a probability density function. But if I wanted to, I could. I just don't want to. All right, let's see what they want us to find out. They want us to find the probability that it lasts longer than 6 years. Now, I know that probability, when I have a probability density function, is just an integral. So I know it's going to be the whoa, I don't want that one. I know it's going to be an integral, and I know it's going to be of the function 1/11 times 1 plus 3 over root x dx. I'm just not sure what those limits are. What number is going to go here, and what number is going to go there? Right? Well, they want this to be longer than 6 years. So that means 6 years is the minimum, my lower limit, and then longer than 6 years means upper limit is as big as it can be, but my model only works out to 9, so that means that my upper limit has to be 9. And now I'll just go ahead and calculate this integral. Okay? So I'm going to drag it over here so I can start working on it. Let's see, that's going to be the integral from 6 to 9 of 1/11 plus 3/11 times x to the negative 1/2 dx. I'm rewriting this root that's downstairs as an exponent so that I can actually find an antiderivative. Antiderivative of 1/11 is going to be 1/11 x plus 3/11. Antiderivative of x to the negative 1/2 is going to be 2 over 1 times x to the 1/2. Remember, when you're finding antiderivatives, you're adding 1 to the exponent and then taking the reciprocal and making a coefficient out in front. So that negative 1/2 plus 1 gives me this positive 1/2 exponent here. And then the reciprocal of that is right there. The 3/11 is just the coefficient that was there. I drag it along. And I need to evaluate this from 6 to 9. Okay? So then that's going to be, I'll do the upper limit in orange. I'll do the lower limit in pink. So plugging in the upper limit, that's going to give me 1/11 times 9 plus, plus 6/11 times the square root of 9 minus, and then I do the lower limit, 1/11 times 6 plus 6/11 times the square root of 6. Simplifying that first piece, I'll simplify that first piece in blue there. That's going to be 9/11 plus 18/11. That's what, 27/11. Right? Minus, then I'll simplify this, but this hot mess is just going to be a hot mess. This is just going to be 6 plus 6 root 6 over 11. So then my final answer is going to be 27 over 11 minus 6 plus 6 root 6 over 11, and that's my probability. But that's a horrible number. I'm going to need a calculator to evaluate that. But if I'm going to end up evaluating it in the calculator, so 27 divided by 11 minus the quantity 6 plus 6 root 6 divided by 11, I get 0.573. So a 57.3% chance that this machine will last longer than 6 years. Let me change that view to always in front. Okay. All right, that's fine, and I can do this all day long, but I'm going to make the following argument. Why don't I just take this original problem right there and put that in the calculator? Why don't I just type in the integral from 6 to 9 of 1/11 plus 3 divided by the square root of x dx, and just have it, oh, I typed that in wrong. Let me try that again. From 6 to 9 of 1/11 times 1 plus, I forgot that 1 plus in there, 3 divided by the square root of x. And close those parentheses with respect to x. And you'll see I got the same answer that I got over here. I don't think I wanted the arrow. That wasn't my goal there. My goal was just to underline it, and I'm still with the arrow. Let's try it again. And yay, it worked that time. Okay. Most of this integration can absolutely be done by hand, but it doesn't need to be. All right, let's take a look at the other two. What were the other two? Now I'm going to need some space here, so I'm going to go ahead and get rid of some of this. By some of it, I mean all of it. Okay, and just put down that answer. That answer was 57.3%, I want to say. Yeah. Okay. If I can set the integral up, I know I can get someone else to do it for me. So what does less than 5 years mean? Less than 5 years means that that upper limit is 5 now. Now it's only valid starting at 4, so it can only be from 4 to 5. Of 1/11 times 1 plus 3 over root x dx. So less than 5 years. Now if I want to get really fancy about it, this is going to find me the probability that my random variable is less than 5. And this one up here found me the probability that 6 is less than my random variable is less than 9. And I can write this out using probability statements. Okay? But that's not what I'm really focusing on right now. I'm focusing on actually setting up the integral and doing the math. Okay? Now I could do this one by hand like I did the other one, but I'm going to choose not to. I'm going to go back to my calculator and see if I can figure out how to do this again. Okay. So let's see, how do I do this again? How do I do this? Okay. I go to my function integrate command. I type in my lower limit. I type in my upper limit. I type in my integrand, which in this case is 1/11, parentheses 1 plus 3 divided by the square root of x. Close those parentheses so the 1/11 gets distributed, and then it's with respect to the variable x is dx, and I get a 22% chance. So 21.97, 21.973, round wherever they tell you to round it, but it's almost 22% chance. Okay? And then what's the last one ask us to do? Between 4 and 7 years. Between 4 and 7 years of 1/11, 1 plus 3 divided by the square root of x dx. That's going to be the probability that 4 is less than our random variable is less than 7. Okay? And what is that going to work out to be? Now I'm going to show you even another trick. Since I've already got that integrand typed in, can I just go back up there, steal it, copy it down here, and then just go through and change those limits of integration from 4 to 5 to 4 to 7, and press enter, and get that that's 62.5%. So there's a 62.5% chance that this machine will last between 4 and 7 years. Well, this isn't too bad. My job here is to find probabilities for a probability density function. Probability density function just means integrate. And I can do it by hand if I want, or I can use some sort of technology. My calculator is wonderful for this. All right. How about this one? The life measured in months of a certain computer part has a probability density function defined as f of t equals 1/2 e to the negative t over 2 for t in the interval 0 to infinity. Up here, our variable was x. There was an x and an x. Now down here, my variable is t. Does that matter? No, it doesn't matter at all. Right? Up there, my interval had a number on the bottom and a number on the top. Now I've got an infinity. Does that matter? Nope, doesn't matter at all. In fact, probability density functions can have intervals that go from a fixed number to a fixed number. They could have intervals that go from a fixed number to infinity. They could have intervals that go from negative infinity to a fixed number, or they could have intervals that go from negative infinity to positive infinity. It just really depends on what's the variable and what does the variable mean. In some situations, negatives won't make sense. In some situations, negatives will make sense. There's no rule that says it can or it can't be. Right? So the fact that this one goes from 0 to infinity just means that this computer part can't last shorter than no time, but could last theoretically forever. Okay? All right, so let's find out what they want us to do. Find the probability that it lasts at most 12 months. That most 12 months means the 12 is an upper limit, so that means the integral from the lowest value, which is 0, I got that from my interval, up to 12. For 1/2 e to the negative t divided by 2 dt. And that's going to be the probability that x is less than 12. I could do this one by hand, but you know me, I'm lazy, so I'm going to use my calculator. I'm going to say, I don't want to do this one by hand. Why did this get weird and get small on me? I'm going to use the calculator, so I'll clear that out. I'm going to go to my integrate command again. I have a lower limit of 0. I have an upper limit of 12. I have an integrand of 0.5 e to the negative 0.5, and I'm going to use x because it's an easier letter to get to than finding t somewhere, dx. 99.7. 99.8 if we round it. So we have a 99.8% chance that this part will last at most 12 months. So less than or equal to. The second one asks, why is it getting small like that? I don't like that. That's weird. Part 2 asks us, what's the probability it'll last between 12 and 20 months? Right, between 12 and 20 months. So the probability that 12 is a lower limit and 20 is an upper limit, that's just going to be the integral from 12 to 20 of 1/2 e to the negative t over 2 dt. I can do that. In fact, I've already got this in my calculator. All I have to do is change my limits. So I'm going to go back up and steal that, copy it down here. I'm going to go over here and I'm going to change those limits. My upper limit is now 20. My lower limit is now 12. And the answer is 0.2%. 0.24%. Looks to me like this part has been designed to last less than 12 months because it doesn't look like there's much chance that this thing is going to last over 12 months. Okay? Now, if you think about this, and if you remember your college algebra, if I were to graph this function, that's a decreasing exponential function. It goes down like this. Okay? And so if this is my horizontal axis t, and this is my vertical axis, which is my f of t, right? Then the probabilities here, and where is this? I want this. The probabilities here, let me shade this. Do you see how that area gets really small really quickly when we move out this way? So the probability of failure is pretty high on the low end and pretty low on the high end, or that this thing won't last very long at all. Okay, does that make sense? Right. My graph is actually wrong. This crosses right there at 1, right? Oops. It crosses that x-axis at 1. So lots of probability down here on the low end, but not too much up there on the high end. So there's a good chance this thing won't last very long. Right. We're at 22 minutes, so I'm just going to call it here, and we'll come back and start with cumulative distribution function later. See you all back here for part 2.